Hello, good afternoon. Welcome back to CS560. So today we will continue our topic in about dynamic programming using the rod cutting problem as an example. Okay, so let's do a brief review first about the problem first. Okay, so the problem is to get the optimal revenue by cutting the rod into several pieces. Okay, and we formalize the problem into this form. Okay, so the revenue for the rod of length n, we express it by the um, maximum elements among a bunch of possible combinations. Okay, so we can choose to cut at the place of length I, right? We cut into a first piece of length I inches, and the right hand remainder is of length n minus I. Okay, and the revenue, the possible or the best, the optimal revenue for length n is the maximum amount.
I got a quick question.
Yeah.
So, I don't know, like this is kind of out of like speaking, but we just got our test grades back and I looked over what the TA graded, and I personally made sure everything worked in like coding wise. And in the last one, it was saying that the peak was n, but it wasn't n. Um, the last one, the recursive one on the last problem, it was like something to k, and k doesn't work because of one. It like works for every case but one case, and that's why I put on my test k minus one and then k plus one for the next one, because I tested every single case, and for one of those cases it doesn't work out.
So you're talking about the midterm question, right?
Yeah, no, because I personally tested myself, and k on the last one,
Yeah.
it doesn't work for one case.
Can we bring that question after the lecture, or we
Yeah,
can?
yeah.
Okay.
Yeah, I'd like, yeah, no, that's fine. Because I just want to go through that.
Yeah,
Okay.
we can have a brief meeting after the lecture. Yeah. Okay. So here's the mathematical expression of the optimal revenue for the rod of length n. So it is the maximum among a bunch of combinations by first cutting to length n and ultimately cut the rest of the rod. And I have the range from 1 to n. Okay, so we basically express the original problem into the solution to the subproblems. Okay, so this is something we called optimal substructure. Okay, so we based on this simplified expression of the Rn or of the solution, we can implement a recursive solution, a recursive procedure that solves the rod cutting problem. Okay, so we basically want to choose among the maximum. So we basically use a for loop to iterate over the possible places of the first cut. Okay, and then we need to choose the maximum value out of these n possible first cut places. Okay, but in order to solve the optimal solution of the remainder, we need to call the function recursively. Okay, so basically we call this function itself on the remainder part, and the length of the remainder is n minus 1. Okay, so last time we have briefly gone through this recursive implementation, and we concluded that this is not a very efficient solution, because there are too many recursive calls, okay? And those recursive calls simply, they just solve the same problems repeatedly, which is totally unnecessary, okay? So if we look at look at this example. So when the input is 4, then the cut rod on 4 will incur these subroutines or incur these calls, the cut rod on 3 and 2 and 1 and 0. And each of these calls will incur their subcalls, okay? So although cut rod 2 is solved here, it's solved again here, okay? So all these recursive calls, they are additional, they are unnecessary calls. So this is basically why this recursive algorithms is not the most efficient one, because it doesn't take into account whether the same subproblems has been solved or not, okay? So, and if we visualize the outcome of these so many repeated recursive calls, it is a very bushy or it's a very wide recursion trees, okay? So if we use the number in that node to indicate the length of the input, the length of the input to the subproblem, then we can see that there are so many repeated nodes because they represent the same subproblems, okay? And this tree, if we need to go over all the nodes in this tree, then the total running time would be basically can be expressed by the recurrence equation like this, okay? So if the input is of size n, then it's the summation of size n minus 1 plus the t of n minus 2, blah, 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 until the smallest subproblem, okay? And we will find that the solution to this recurrence can be expressed by a exponential function. An exponential function is an extremely inefficient function, or it grows really fast, okay? So that is why this is not an efficient solution, okay? And the solution to the Fibonacci number, if you recall that for Fibonacci number, we use the recursive solution, which is also have the similar characteristics as this solution, which is also by the grows by the speed of exponential function. Okay, so we basically need to think of a better solution using the dynamic programming solution. So the problem that dynamic programming why is the for loop not considered during the runtime analysis? Okay, so basically the for loop, if you look at the for loop, it ranges from 1 to n, right? The for loop ranges 1 to n. So in order to solve t of n, we need to solve t of n minus 1, right? Because that is the case where I equals 1. And when I equals 2, in the second iteration, we need to solve t of n minus 2. We are actually considering the for loops, okay, until I reaches n, which means in that case, we need to solve t of 0. Okay, so the t of n indicates the original, the solution to the original problem, and it is a summation of these subproblems. Okay, this is the outcome when we consider the for loops. Okay. But since the T of n can be further expressed by T of n minus 2 plus T of n minus 3. Okay, so and all of these terms can be further expanded. So that is basically why this solution to T of n can be expressed by a exponential function 2 to the power of n. Okay, so I didn't give a proof of why this long equation equal to the 2 to the power of n, but I think we can actually prove it. Yeah. So from the tree, judging from the tree, it is a very very wide tree. So for each node, it expresses so each node expanded to its full stretch, like the 3 expanded to 2, 1, 0, and 2 expanded to 1, 0. I think by observing the per level summations, we can by counting how many nodes are there, we can basically prove that the total number of nodes is 2 to the power of the input size. Yeah. Okay, so that's a good point, good question though. Anyway, so we want to avoid this and use a dynamic programming solution to solve the original problem. So the idea is that we want to save solutions to the subproblems because we don't want to solve them repeatedly. So why not, after each time we solved a solution for the first time, after we solved it once, we will save the results immediately. And later on, when we meet the same problem, we will just look up that solution without solving it. Okay, so we need to use some strategy to look, or use some data structure to look up the solutions to the subproblems rather than using the recursive calls to recalculate, to recompute. Okay, so we basically need to use some additional memory space in the exchange or computation time. So this is a typical time memory trade-off. Okay, so there are two ways of implementing the dynamic programming solution to the rod cutting problem. The first one is called a top-down method. Okay, so and the other one is a bottom-up solution. So compare these two methods. I think the bottom-up way is easier to understand, and the top-down still uses a recursive call in the implementation, but it's not a recursive call, but it's the top-down manner of thinking of the problem is not that intuitive as the bottom-up method. So we'll see the difference here. So the top-down, and it is called the top-down with memorization, which means that we basically write the procedure recursively in a natural way, okay? But we modify the parts that each subproblem is, after each subproblem is solved, okay? We need to save the results of each subproblem in an array or hash table. So in this case, in this particular implementation, we use array, okay? And now we need to first check whether it has previously solved this subproblem. Yes or no. Okay, if we have solved it, then we will simply return the saved results. If not, then we need to compute the value in the usual manner, which is a recursive manner. Okay, so this procedure is called memorized, and the term memorized term is just a different name for memorize. Okay, So in the implementation, we need to define two procedures or two functions. The first function is called memorize cut rod. Okay, so it takes input the P. So remember the P. The P is the table, is a table that contains the unit price for each length, for the rod of each length. Okay, it's just a constant table. It gives you the information of that is necessary to compute. And N is the length of the input rod. Okay, so we defined a new array, auxiliary array called R to store the results of the subproblems, and it's initialized to negative infinity. Okay, because the negative infinity is the smallest possible, smallest ever number. Okay, when this infinity is compared to any other number, it always smaller. Okay, and then that's all of it. Okay, so this function simply does the initialization and it returns the results of a helper function. And this helper function called memorize cut rod auxiliary. Okay, and this function, so basically we need to focus on this function. Okay, and this function takes the R as input, and that R is initialized to infinity. So this R will be used to add some external memory space to store the results. Okay, okay. So here's how this memorized cut rod arcs look like. Okay, so the first two line of code, if we look at it closely, it's just a if condition to check whether the solution exists. Okay, so we simply check the value of Rn because the input is n. Okay, if Rn is greater than 0, then it means it's not the negative infinity initialized. Okay, so that means the solution already exists. If that solution exists, then we just simply need to return it. Right? So if this is not the case, then we need to solve it. Okay, so in the next line of code, we will compute the desired value in the usual manner. Okay, just like the recursive solution to the cut rod problem. Okay, and the if n equals 0, it's for the smallest case. So if the input is of length 0, then we simply define the 0 revenue and save the result to the function, to the corresponding place in the R space, in the array R, right? And if n is greater than 0, then that means the input's rod can be cut, can be divided. Okay, so we use a for loop that ranges from 1 to n to iterate over all possible places for the first cuts. Okay, and then we compare among this bunch of choices to choose the maximum elements from pi, by comparing the value of pi plus the memoized cut rod function over the rest part of it. Okay, so compared, so this is still a recursive call here, but compared to the cut rod original recursive solution, these parts are additional, and this part is also additional. Okay, so these two magical parts helps us save time, right? So this line 8, it stores the value q, which is the solution, to the right place, which is R of n, right, before the solution is returned. Okay, and the first two line of code checks whether the solution exists. If yes, then this solution will be returned. Okay, so that is the difference from the memorized cut rod arcs with the original cut rod recursive solution. So now next we'll use an example to see basically how different the outcome would be given some simple input examples. Okay. So we'll choose a very simple example, which has the input length equals 2 first. Okay, so the table shown here is the P. Okay, it's the constant P table. Okay, and I copy the code for the helper function here, memorize cut rod aux here. Okay, so this is how the revenue array look like. Okay, so it's all initialized to negative infinity from for the 3 elements. Okay, so the initial call is like this. The input is 2, so the arguments looks like this: n equals 2, and p and r. Right. So the q is initialized to 0 because n is not 0, because this condition is not satisfied, right? Because n is 2. So q starts from negative infinity, okay? And then we will go to the for loop in line 6, okay? The I will iterate from 1 to 2 because n is 2, so there are only 2 iterations in the for loop. Oh, so if we dive into the first iteration, I equals 1, right? And the q needs to be chosen among first negative infinity, because that is the older value of q. And the result of p1 plus memorize cut rod aux of p1r, and 1 is the result of n minus I. Because I is 1 and n is 2, so the result here, the argument here is 1. So we are basically comparing these two. Okay, so now we have the second, we have a recursive call here. Okay, so recursive call with inputs n equals 1. Okay, so we will dive down into the recursive call, step into the recursive call. So in that recursive call, because the inputs now, let me use a different color. Because the recursive call has input 1, so the q will still be initialized to negative infinity. And it will be compared with p1 plus memorized cut rod aux on the input 0. So this is the second recursive call, right? Within that first recursive call, there's another recursive call, but this time the input is even smaller with 0. Okay, so this is a very special recursive call because n reaches 0, which is the base case, which means within this recursive call, the line 3 to 4 will be incurred because n equals 0. So q will be 0, and this q will be returned. Okay, all right, so the q is 0, and the value of q is saved to R0 because of the code at line 8. Okay, before q is returned, it will be saved. So R0 is now modified. Okay, R0 is modified. After R0 is assigned to be 0, then this negative infinity is changed. Okay, and then this q equals 0 is returned. Okay, and it turned from the second recursive call to the first recursive call. Okay, so the results of choosing among the maximum elements between negative infinity and the 1 plus 0 will return 0, which is the value of the blue q here. Okay, so after the orange q is returned, the value for the blue q can be computed. Okay, so this blue q is 1, and this q is also returned to the upper level. Okay, and before this blue q is returned, it's also saved to the array R1. Okay, because of the line 8. Okay, any q, before any q is returned, it's saved to the corresponding place in R. Okay, so R1 is modified. So that's why we have this updated table here with both R0 and R1 modified, which means the subproblem of size 0 and 1, they are all now solved. Okay, we don't need to solve them again in the future. Okay, so now we need to return the black Q here. Black Q is computed by comparing between negative infinity and the summation of 1 plus 1, which is 2. So this black Q is 2. Okay, but okay, so this black Q is not returned yet because we are just done with the first iteration. This is the first iteration of the for loop here, line 6. And this I needs to iterate over 1 to 2. Okay, so the second iteration I equals 2, right? And in this case, we need to compare the older value of Q, which is 2 because it's computed here. The black Q is computed here. We need to compute this Q with the value of P2 plus optimally cut the rest part, which is length 0. Okay, so this time we already, when this second time, when this memoized cut rod aux function with input 0 is called, the the first line of code is triggered, okay, because R0 is now already greater than 0. It's no longer an infinity value because it's solved before in the previous iteration. So this recursive call will directly return R0 by look up the table. Okay, so the black Q compared, the results of computing the black Q here will result 5, the value of 5. Okay. So after the first, the 2 iteration is done, we have the solution for R2, and we will save the value to R2, which is 5, and return the value of it. Okay, so this basically shows the using an extremely simple example showing how the cut rod aux function works. And I think the dynamic part happens here, right? Happens the second time we need to call the memoized cut rod aux on input 0. So because when this time is called, it's already solved. The R0 is solved. So we simply need to look up the table, right? And then return the results. And hopefully this helps you understand the procedure. And if you think you need some extra time to understand the code, you can read the slides after the lecture and watch the video again. Okay, so in the next slide, we will look at a slightly more complex. We just increase the length by 1, and we will go through the procedures relatively a bit quickly. Okay. All right. So because now we have input length, the length of input is 3, right? And all these, so we have 4 elements in the revenue array, in the R array, and it has 4 infinity values. Okay, so the initial call would be n equals 3. Okay, and Q is initialized to infinity. So this time we will have 3 iterations because the input is 3. So I will range from 1 to 2 to 3. Okay, so in the first iteration, I equals 1, and there will be a recursive call with inputs length 2. Okay, so this is within this call, there will be 2 iterations, which I identified by the color blue color. So that's indicating that it belongs to this recursive call within this recursive call. It doesn't belong to the upper level. Okay, so within this recursive call, I ranges from 1 and 2. We have 2 iterations. Okay, so the results will be returned to the upper level, to the black iteration, first iteration in the black color. Okay, and in the second iteration, I equals 2, we will incur another memorized call, this call. Okay, so now we pay attention to the input. It's size 1. Okay, so it's already solved, right? So we will simply return the results that's already solved within this step. Okay, but do not incur further recursive calls. And for the third iteration, there will be another call to the smaller problem, which is of input length 0, but it is also solved within this step, right? So it will just look up from the table. Okay. All right, so these longer examples shows more steps that the recursive calls is replaced by the lookup operation. Okay, and the lookup operation happens in the first line of code, the line 1 and the line 2. It checks whether the elements exist or not. So basically, the returned results will be a complete array that contains the optimal revenues for all possible input lengths that's below the input length. Okay, so this return the results also indicates that, because our goal, remember, our goal is just to know about R3, right? We just want to know if the rod is 3 inches, what is the optimal revenue, right? We just have that one question in our mind. But the returned result contained the solutions to all the subproblems, length 0, length 1, and length 2. And that means this problem, in order to solve the problem of length 3, we must solve all the subproblems of length 2, length 1, and length 0. Okay, so that gives us some hints about implementing a second bottom-up way of dynamic approach to rod cutting. So in order to solve length 3, why not we start from length 0? We solve length 0, and then we solve length 1, and then we solve length 2, and finally we solve length 3. Okay, right? Because the larger problems rely on the smaller problems. So why not we start from the smaller problems? And that is the idea of the bottom-up dynamic programming approach to the rod cutting problem. Okay, so it's based on the observation that the particular subproblem depends only on solving smaller subproblems. Okay, so we should solve the subproblems in a size order. We solve the smallest first. Okay, so after the smallest is solved, then the bigger ones, when we solve the bigger ones, we don't need to solve the smaller ones again. We just refer to the results. Okay, we should, when we solve a particular subproblem, we should all have already solved all the subproblems that it's depend on. Okay, so here is the bottom-up cut rod procedure. Okay, so now we don't need a auxiliary helper function like the top-down method does. Okay, so we just use the P at the end and its inputs. Okay, and the first line, 2 lines are initialization. Okay, it creates a new array which is similar to the top-down, and R0, R from 0 to n to save the solutions to all the subproblems, okay? And we just initialize the smallest subproblem, R0, because this is the smallest case. There couldn't be, it couldn't be any smaller, right? So next, so look at this for loop. It's a, first of all, it's a nested for loop, right? There is the outer for loop. The outer for loop lets j to indicate j to iterate from 1 to n, okay? And the purpose of this outer for loop is to solve each subproblem of size j, ranges from size 1 to size n. And we have to solve that in such an order, in increasing order, okay? Because solving the problem of size 1 relies on the problem of size 0. And we already know the solution to 0 is there, it's initialized, right? So that is the way we handle the dependencies. And then after we solve 1, we save the result to size 1. And then in the next iteration, after we, when we need to solve the size 2 problem, we just simply look up the solution to the problem of size 1. Okay. All right. And the second, so let's look at the body of the outer for loop. Let me use the different color to highlight. Okay. Within the body of the first for loop, okay, so this is the body of the first for loop. We first initialize some q, and we use a second for loop, the inner for loop, to solve this subproblem of size j, right? Within each iteration of with the brown box, the j is fixed, right? The j is some value. Okay, now how do we solve the subproblem of size j? Is that we use a second loop counter, which is I, to iterate from 1 to j, right? Because we want to solve the subproblem of size j, then we need to choose the place to have the first cut among the rod of length j, okay? And we have to choose among the possible, we need to choose the maximum revenue out of this j possible first cut, right? So we need to have the maximum function placed over all possible i's, right? And for each I, we have the combination of pi plus r j minus 1, okay, j minus I. So this is the lookup, where the lookup operation happens, okay? So the approach we use here to solve the problem of size j is actually the same as that used by the cut rod, okay? But the only difference is here, the only difference is the red box here, right? If you compare the procedure with the cut rod function, this code, line 6 code, it is not a recursive call. It directly look up from the table instead of making a recursive call, okay? So use a particular example with j equals 1, okay? So when j equals 1, that's the first iteration, right? When j equals 1, and I will iterate from 1 to 1. So within the only iteration, this r j minus I is actually r0, right? And r0 is something we already know, it's a 0, okay? So this doesn't conflict, because whenever we want to refer to the elements in R at the index j minus I, it's already solved, okay? Because it's a smaller problem compared to j. J minus I is always smaller than j, okay? So when we try to solve j, we need to look up the solution to the smaller problem, which is j minus I, which is acceptable because we already solved the smaller problems, okay? because I ranges from 1 to j, and any smaller problems is already solved within the previous iteration. Okay, so this is the bottom-up cut rod problem, which I think which I think excuse me. So which I think is easier to understand than the top-down method, because it defines clearly the smallest problem that needs to be solved first. Okay. So one thing we need to keep is that after each problem of size j, subproblem of size j is solved, we need to save the solutions. Right. So without this step, without a step at this line 7, the future iterations will never know that the size j, the older size j, has already been solved. Right. So in order to make the algorithm work, we have to have this setup. Right. After the solution to the problem, we need to solve it, save it at once. Okay. So again, let's go through this example. Use n equals 3. So after the initialization, we have a table like this. So I give the 0 to all the values because it doesn't matter, because we just need to know that R0 is initialized to 0. Okay. So the first iteration is of j is 1, right? And I iterates from 1. So the equation of choosing the maximum elements from negative infinity with and P1 plus R0 results in 1, okay? And that means R1 should be 1. And R1 will be saved to the R value, okay? And then in the next iteration of j equals 2. And here, I should iterate over 1 to 2, okay? When I equals 1, we can look up the value of R1 here, right? Now we need to look up R1, but we already saved R1 in the previous iteration. So this is a valid operation, okay? And then we have Q equals 2. And in the second iteration of I, Q should be compared with 2 and the new value, which is P2 plus R0, which is larger, okay? So that means R2 needs to be 5, okay? And we save that new value to the R, okay? And then in the last iteration of j, we need to let I iterates from 1 to 3. So in the first iteration of I, it refers to R2, but R2 is already computed here. So it's a valid operation. And we just return the value of it and it got 6. And in the next iterations, we'll have the correct Q computed. And then we will store the maximum value of Q to R3. And eventually the whole table or the whole array will be returned, okay? And this time we can clearly see that in order to solve R3, we need to solve R1 first, and then R2 first. And lastly, we solve R3. So that is the clear, very clear dependency between these subproblems. Okay, and we only solve each subproblem once, because when we want to know the results of the subproblem in the later stage, we simply use the array to look up that value. Right? We didn't do any recursive calls, so that will significantly save us time. Okay, that is the correctness of the two dynamic programming approaches. So when it comes to analyzing the running time for two versions, clearly the second bottom-up manner bottom-up approach is easier to analyze because it's two for loops. Okay, due to the doubly nested for loops nature, we can come to the conclusion that it runs by the quadratic running time function. Okay, because the number of iterations of the inner for loop is j, right? And j equals 1 to n. So it's basically an arithmetic series. Okay, but the top-down method, how do we analyze the running time? It actually requires some technique called aggregate analysis. So which is not required here. So, but we will find that they will result in same running time performance or same total running time. But from the perspective of avoiding recursive calls, I think the bottom-up way should be preferred because it doesn't incur any recursive calls. And a recursive call means that you still need to use the stack, and it will cost you extra space and time. Okay. So finally, let's look at the subproblem graph, which is a way to analyze the dependency, to demonstrate the dependency between the subproblems in dynamic in this rod cut problem. Okay, and it is basically a variant of the recursion trees. Okay, in recursion trees, we split each node whenever we want to solve one problem by solving all of its subproblems. Okay, but in the dynamic programming problem, we basically just want to solve each node once. Okay, so the connections between the nodes, the arrows shows the interdependencies between the subproblems. Okay, so the graph means that to solve R4, we need to depend on R3, R2, R1, and R0, and solving R3 depends on 2, 1, 0, and solving R2 depends on 1 and 0, and so on. Okay, so in this case, all the subproblems are solved once. So we can actually think of this subproblem graph as a result after we merge all the nodes with the same values in it in the recursion tree. So on the left, this is the tree of the very inefficient cut rod function. It will result in a very broad, a very wide recursion tree. So what if we just, say, merge all the twos, right? And we merge all the ones and merge all the zeros. Okay, left 1, 0, all the zeros. So after we connect these nodes of the same values together, we will have something like this. So this is a analogy showing that, this is a kind of a way to visualize how the same subproblems are only solved once because all the nodes converges. It doesn't diverge like the recursion tree shows. Okay, so if we use the same technique to analyze the same subproblem graph to analyze the Fibonacci problem, we can have also a similar merged graph. Like we can think of the Fib1 as our first subproblem and the Fib2. And in order to compute Fib3, we rely on 1 and 2. And for Fib4, we rely on 2 and 3, right? And 5, 6, and so on. So this is a very typical subproblem graph for the Fibonacci problem. Okay. All right, so I think we are reaching the last problem, last issue with the rod cutting problem. Okay, so far we have returned the optimal revenue in R, right? R is a number. It's the total money we can get by selling that input rod. Oh, so it's just a number, but it's not the, it doesn't contain all the information, like what is exactly the optimal way to cut, right? We want to have that information as well, okay? So it's also quite straightforward to achieve. We can extend the algorithms to record not only the optimal value, but also the choice, the place to cut, okay? We simply need to modify the procedures a bit, okay, by changing some lines of the code. So using the bottom-up way as an example, okay. So what's different compared to the original version is here we have an additional line. Actually, we replaced the maximum statement with this if statements, but this if statements, it does the same thing. It compares the queue with the new candidate value. So this candidate value is the choice of to have a first cut at length I and plus the optimal revenue of the remainder parts. Okay, so if this new candidate is greater than the original queue, then we need to update the queue, and we need to record the place to cut, right? Because I is the place to cut, so we need to record that choice, and we put it into SJ. S is another new array. Okay, S is another new array that indicates the optimal size of the first piece to cut off. Okay, it indicates where to place the first cuts. Okay, so now if we look at the example, the output example here. Okay, and calling the extended version of bottom-up cut rod, given input size equals 10, will give us a very complete information. Okay, so we have S arrays here. Okay, so it records the place to give the first cut. Okay, so if we look at the value S9, which is 3, it means that in order to get the optimal value from a rod of size 9, then the first cut need to be of size 3, right? And 9 minus 3 is 6, right? Then the remaining part is 6. So what about the rest part of the cut? How do we cut the length of the remainder part of size 6? We simply need to refer to the S of 9 minus 3, which is S6, right? And S6 equals 6 means that for an input length of 6, we don't need to cut it. Okay, so that table contains the information to a complete solution to any input size. Okay, so in order to print those complete solutions, we simply need to first call the extended bottom-up function to get the results, which is two vectors, the R vector and the S vector. So when given the input n number, we simply print the step for each S elements. We first print Sn, and then we will need to update the n by minusing the S, by removing the first cut, right? The first cut is Sn, and the remainder part is n minus Sn, and we will continue this step until n is 0. Okay, so this will print the solution for the table given any inputs. Okay, so if we call the print cut rod solution on 9, it will give us like this. It will print 3 and then print 6, which basically tell that we need to first cut at the place of 3" and 6". Okay. All right. So finally, let's do a bit of recap of the conditions that needs to be satisfied when we want to use dynamic programming. Okay, so first of all, it's the optimal substructure or optimal structure. So it is a property of a problem that if an optimal solution to the problem contains optimal solutions to the subproblems, then we can probably think about whether dynamic programming is a proper choice or not. Okay, so whenever we have observed such a property, we can think that DP might apply. Okay, but it's not necessarily so, because another ingredient is that there should be overlapping subproblems. Okay, the space of subproblems must be small. It should be at least discrete. Okay, there should be plenty of overlaps among the subproblems. Otherwise, like the sorting problem, like if we cut the inputs into two segments and we solve the two segments recursively, then there's no way to use dynamic programming because the resulting two subproblems, they don't necessarily overlap. Okay, the subproblems are not discrete. So we want the subproblems to be discrete and they overlap a lot. And that is the two conditions that DP can apply to. Okay, so if the subproblems do not overlap, if each time we divide, a brand new subproblems will come up, and then basically we don't need to, we cannot use DP, but we have to use a divide and conquer approach. Okay, so that is so much for the dynamic programming solution to the rod cutting problem. And in the next lecture, next week, we're going to cover the matrix chain multiplication problem, which is also solved with a dynamic programming approach. Okay. Yes. So now let me stop the